It is a very cool idea, the last talk. So, date's wrong. Alan Miller is the lawyer, so there are a few mentions of legal cases here. I don't know actually what they say. These are his slides. So the way I plan to do this is, there's 4 papers here. I'll try to talk about some of them. I'll see how many I can get over. Some of them are solo by myself. Some of these are joint with Alan. So this is, most of you know about gerrymandering, and most of you know it's one of these sensational things, right? So you always need these crazy pictures. There was this guy, I guess he was a governor of Massachusetts way back in the 1800s. His name is pronounced Gary, Elbridge Gary, and he created some kind of congressional district, and a political cartoonist drew a picture and said, whoa, this looks like a salamander, right? And so they called it the gerrymander. So this is, everybody knows what gerrymandering is. It's when you strategically draw districts in order to influence the outcome of a vote. Okay, we don't really know what it means to non-strategically draw a district, but this is just kind of an informal phrase, right? Gerrymandering. So this is the sensational stuff. So when I was at Caltech, we had a lot of neuro talks. The neuro guys would have the pictures of this guy who had the railroad spike in his brain. This is kind of what the political science counterpart. So this is what a gerrymandered district looks like. Chicago, all the way over here, comes up and picks up a bunch of people.
All the black stuff is one district?
That's one district.
Which number? Do you have the district number down here?
Yeah, just 4th District, Illinois.
Wow.
This is supposed to shock you, right? It's supposed to be surprising. And so this one doesn't look so bad, but what it's doing is it's picking up a bunch of cities. It has these kinds of fingers that go out here and pick up cities that you're supposed to think that's bad. This one is supposed to think it's bad. This one again, it doesn't look so bad, but really you have these 2 populated areas separated by, here I guess this is probably rural, right? This is Pennsylvania, so this is yeah, and then, but over here they're kind of joined. So you get the idea, right? These are like messy looking things in general. So the question is, doesn't look legal, but somehow it is, right? That's what the lawyers, huh?
You didn't show Texas.
It's probably coming up here. There's all kinds. It doesn't matter, you know. You pick a state, and they have these all over the place. So this is Maryland. This is going all through Baltimore. I think this is where I grew up around here. Huh? That's your district, huh? So you're down here with the folks in Annapolis.
I thought there were rules which said they had to be contiguous or something like that.
No, these are all contiguous. So contiguous.
So there's some little string out there that connects.
There's like a strip of land along the highway.
Yeah, contiguous means mathematically connected or pathwise connected. So, yeah.
Inch by inch.
This is formally contiguous, right? This might be was this you were talking about Georgia, or was it Texas?
No,
one of the southern states.
I was talking about
Okay.
Contiguous means you don't need a passport to get from one place to the other.
And so this is somewhere in Los Angeles. Yeah, it looks like LA. I have a million of these, actually. Okay. Yeah, so what can we do about it? The first thing I'm going to go over is a couple of theorems that I wrote up maybe 10 years ago or so. So what's the feature of all of these districts? Well, they were drawn under a system of majority rule. Okay, so the first question that I wanted to ask was, what happens if we don't want to go with majority rule? We want to try something else. Okay, and is gerrymandering going to be a problem more generally? And the answer is yes. Yes and no, and that's going to be on the next slide. I don't know if you guys are familiar with this notation. This is boldface n. When you write it like this is just the natural numbers. So it's 1, 2, 3, and all the way up to infinity. And so this is just a way of indexing potential agents. So you never imagine that you have an infinity of agents present at any given time, but you do want to be able to consider arbitrarily large sets of agents and apply a voting rule to arbitrarily large sets of agents. So at any given time, I'm just going to consider a finite subset, n, of the set of natural numbers. And this is supposed to indicate just a group of people. Okay, these are just names. Each number index is a person.
So an individual is really a point in a geometrical structure.
I'm going to get there. I'm going to get there. But an individual here is just a name.
Is it
So I mean, I could call this the natural numbers. I could pick any countable set. It's just.
So it's not really.
So you're number 3. You're number 4. You're number 5.
Okay.
But the number doesn't mean anything. That's going to be. So this is kind of fancy notation. What does this mean? Well, this is a big U. This just means I can pick any subset of voters, finite subset of voters. X, this is just things you're voting over. I want you to think of, what do you guys like to vote over? Let's say left wing, right wing. X, taxes, no taxes, right? It's just things people vote over. Yeah. I'm not a really applied guy, right? I'm going to be honest. Okay, so this just says pick a subset of voters and assign them a vote. So there are no preferences here in this model. You could put them in if you wanted, but there are no preferences. People just go to a ballot and vote for their favorite thing. And the output of a voting rule is just one of those alternatives that they could have been voting for. So you might have a society consisting of agents 1, 2, and 3. This guy votes for tax. This guy votes for tax. This guy votes for no tax. And I apply my rule to this, and maybe it says, okay, let's have a tax. That would be plurality rule or majority rule or something like that. Is that relatively clear? I mean, it's complicated notation. I think the next page is even more complicated. But so what are some basic properties, very, very basic properties we would expect a voting rule to have? Well, you guys have all heard of the Pareto principle. The kind of counterpart of that would be the unanimity principle that says if I pick a set...
Let me make sure that I understand. So a vote basically is just an alternative that I say this is it.
You say this is it.
Each
Yeah.
individual
Yeah.
says some object.
Yeah, you say, I want a tax. You say, I don't want a tax. You say, I want a tax.
I want downtown LA.
Yeah, yeah.
Yeah, okay.
Okay, so if everybody wants a tax, let's have a tax. That's what unanimity says. If everybody doesn't want tax, we have no tax. And this is actually a real thing. I saw some guy on TV say, you know, we shouldn't have taxes.
No, X is in elements.
I'm going to get to that. I'm going to get to that. I'm going to get to that next, after this. But I want you, right now, I want you to think X is totally abstract. N elements, infinity elements, a billion, infinity plus 1. You know, okay. Anonymity, this is not written properly here, so don't pay attention to this. This says the names of people don't matter. So if I take 1, 2, or 3, and this guy votes for a tax, this guy votes for a tax, and this guy votes for a tax, or if I take 2, 4, and 3, let's say, and this guy votes for a tax, right? That means that if I apply the voting rule to either of these two profiles, the outcome is going to be the same. It's a tax, right? Okay, so it's not anonymity in that you don't know who voted for what. You might very well know who voted for what. The other condition, there's one more condition I want to talk about. We call this gerrymandering proofness. This is a little bit more complicated. I want you to think of this as kind of saying that direct and indirect democracy should coincide. So if I take everybody's vote and I aggregate them into a social alternative, that's what I'll call direct democracy. Indirect democracy is going to work in 2 stages. Right? First, I'm going to partition the people. So a partition is just, I take the people in society, so any given society, I have my finite set n. I partition them, that means I take n, right, and I cut it up into pieces. It's really a system of districts. Okay, so everybody's in exactly one element of the partition. What I'm going to do then, and this is where the notation is confusing, I'm going to take any given element of the partition. Let's say I take n1 here, so I have n1, n2. The partition has to be finite, but that's obvious because the set of agents at any given time is finite. So I'll have my votes here. Let's say I have x1, x2, x3, etc. And let's say I'm just dealing with a set of agents 1 up to n. What I'm going to do is I'm going to take the agents in group 1, and I'm going to put them together, and I'm going to apply the rule to these guys' votes. Okay? Then what I'm going to do is I'm going to replace their votes with the outcome. Okay, so this is like saying you take Maryland. Maryland said they don't want a tax, so I'm just going to treat everybody in Maryland as if they said they want no tax. And I do that for each element of the partition. I take the rule, I apply it to that element of the partition, and then I replace everybody's vote by what the rule recommended. Yeah, it's like an electoral college. And you know, in this model here, I have the same voting rule is applied at both stages. Turns out it doesn't matter. You could have different voting rules applied at both stages. Is this clear? Because this is kind of the main, so this is the main idea behind what I call indirect democracy. Okay, so what I do then is I get this replaced system of votes, a new system of votes. I then apply my rule to that, and then I should get the same thing that I got from the direct democracy. So indirect and direct democracy should coincide.
Will you explain why that's gerrymandering?
Why is it gerrymandering proof? Well, it's a very strong type of gerrymandering proof. Okay, this is saying if I put everybody in one district, it's essentially the same. So it's a very strong. This is the strongest possible. It's the strongest possible notion you could come up with, and so any notion that you could invent is going to satisfy this. So if you can come up with something weaker and get some theorems, great.
In some way, the nature of the partition doesn't matter.
That's right. I mean, I've been able to establish the results in the case when we require the partition to all be, to the elements of the partition to be equipopulous, so that they all have the same number of agents. But it's a very strong property. So I have two theorems. These are a bit complicated, but not too complicated. So everybody knows with Arrow's theorem, you require that there's a finite set of people. Everybody knows that, right? As soon as you drop the assumption that there's a finite set of people, Arrow's theorem breaks down. It doesn't break down in an interesting way, but it breaks down. Here, there's a distinction between a finite set of alternatives and an infinite set of alternatives. And actually, I think the distinction is qualitatively interesting here. So with Arrow's theorem, you have an infinite set of people. Then you get something called an invisible dictator. It's like it's a bizarre mathematical construct. And there's no reason you would ever need to know something like that. I guess if you were an applied person, you would. Have you guys dealt with invisible dictators? No, there's no reason. there's no reason. So this looks complicated, kind of complicated. So if x is finite, we have an impossibility result in some sense. So what I'm going to do is I'm going to take those three properties and show what the rule has to look like. So let me just show an example. I'll go back over here. If x is finite, let's say x is equal to ABC. Every rule satisfying those three properties is identified with something called a partial order. A partial order is a lot like it is a binary relation, and it's a lot like a preference relation, except not every pair of alternatives has to be ranked. Okay, so there's some indeterminacy if you want. And the partial order is going to have the property, I don't know if you guys are familiar with this kind of notation. This just says, this will be a picture of a partial order. This says that C is lower than A in the partial order, C is lower than B in the partial order, but that A and B are incomparable. Now this partial order is going to have the property that for every pair of elements, there is a unique greatest lower bound. Okay, so this is I could extend this, I could put D, whatever. But here, A and B have two lower bounds. It has C and it has D, but it has a unique greatest lower bound. That's called a semilattice. This in mathematics, they call it a semilattice. It generalizes something called a lattice. There's a unique greatest lower bound. The theorem says that if a rule satisfies those properties, then there's an order over X which renders this ordered set into a semilattice for which the rule always recommends the greatest lower bound of the set of alternatives which receive votes.
So basically you're saying that I don't know whether I like to do X or Y,
Yeah.
but I know both of them are better than Z.
Well, this is not a preference. This is more like a V. So the way I want to interpret
I
this.
understand
Yeah,
that.
yeah, yeah,
But
yeah.
but Z in some sense is a lower bound than whatever.
That's right. That's right. And so the way I want you to think about this is, what does this mean? This says that if let's say I take a profile where everybody picks B, so B, 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 that means we're going to select B because the greatest lower bound of B is B. Okay, if I take a profile where I have B, C, C, well, the greatest lower bound of those two things is C. And if I take B, 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 C, the greatest lower bound of those things is C. So effectively, one person is enough to veto B and to attain C. So the interpretation of this rule is that, or the interpretation of this result is the only way you can eliminate gerrymandering if you have a finite set of alternatives is to give everybody veto power. That's how I interpret this. I don't know if that makes sense. Raise your hand if you're totally confused.
Can you just repeat it?
Yeah, yeah. I can repeat it. I'm going to go over another I'm going to do the example again. That makes it easy.
Essentially an impossibility.
It is an impossibility theorem. So you have, according to your rule, you have a semilattice. So I'm going to draw an example of one here. Let's say D. And in fact, I'll even put E up here, whatever. Something like this. And I could put F over here. The main thing is that every pair of alternatives has a greatest lower bound. Okay, so what happens if everybody votes for A? If everybody votes for A, the greatest lower bound of this singleton point is A. Okay? But now suppose one person out of the entire group, and this could be, I wrote 5 A's here. I could write 250 billion or trillion if I wanted. One person out of the entire group says, I'm going to change my vote to C. Well, then the set of things that receive votes is A and C. Therefore, the greatest lower bound of the set A and C becomes C. So the outcome of the rule, as soon as one person changes their vote to C, and everybody else picks A, becomes C. Okay, so that person is effectively vetoed A. So this is essentially the idea here is that everybody gets veto power. So I like to think of these things as being a priority. This relation is like a partial priority, if you want. The thing with the highest priority, in some sense, gets votes. So the thing with the highest priority that gets votes gets implemented in some sense, but that's very informal. I see you're not too happy about that. You don't like the story? The other part says, is this okay? I mean, I know this is a lot if you don't know lattice theory. It's hard to get all those ideas in your head, so.
So is the intuition that if the gerrymandered result would create a different policy result than the removal of the gerrymandering line, then you have to go with the preference of the person who's disadvantaged? But is that why it's gerrymander proof? Is that what you're saying?
Well, I'm saying this is gerrymander proof, and only this is gerrymander proof.
No, I understand, but is there a reason that...
The reason? I have a theorem. This was a surprise to me, I proved it. I actually didn't know what I was going to get. I'm not good with intuition, but in some sense, you're giving everybody voting power, like 100% voting power.
What it is he's saying the following. Look how horrible it would be to avoid gerrymandering. He says that you have to find the lowest common denominator of everybody. So what you're doing is you're finding, the rule says, can I find a condition where it would say that's unanimity.
In some sense.
Unanimity is the lowest common denominator.
In some sense, I like to think of it as giving everybody perfect voting power. You can't kind of split them up into a tiny piece, or you can't, I don't know if that makes sense.
Basically, you're saying
you can't,
You're saying the only thing that would prevent me from performing committing karate
Right.
is if you have this kind of unity.
That's exactly right. This is exactly, it's like a unanimity rule. That's what this is. So, that's the only way if you have a finite set.
So one of your partitions, however you do this, one of the partitions that has to be okay with the rest of it is that everyone's in one group and C is in a group all by himself. That's a partition.
That is a partition.
that has to be equivalent to him being part of the group where he might get replaced by somebody else's preference. 'Cause
That sounds, yes.
replacement thing.
And we're constructing a
And the
proof.
only way that you're gonna allow not replacing him to be
The proof.
equivalent to
So
replacement.
the proof is trivial for two alternatives. I think this is what you're saying. Yes, it is.
Okay, now, let me ask
yeah.
one more question. Does this generalize the case where this is not a partition of people?
You want to go to Plott's path independence. This is Charlie
I
Plott's.
was just asking a question, that's all.
I guess so. I guess so, right? Yeah, I think so.
I didn't hear what he asked.
He asked,
I
does
would
this
say
generalize?
yes.
I mean, the question.
Yes. Would you think it's yes?
So the question is,
Question is,
his question was whether this generalizes to the case where it's not a partition. I'd have to change this gerrymander proofness requirement somehow, because remember I talked about replacing everybody's vote by the vote that was chosen for their element of the partition. Well, now if they're in two different elements, what do I replace it by? But
It was still a group.
yeah, but if he's in two groups, which one should I? Yeah. So, but yeah, I imagine something like this would still hold. I mean, this is the stronger you make the condition, right? Either it's going to hold, or you're going to have a totally empty set of rules.
The answer is yes.
Yeah, I think so too. The other thing is kind of more interesting. This notation you may not be familiar with. There's this concept in mathematics of rational versus irrational, which you probably know, right? Numbers, rational? Yeah, okay. This just means rational. I think I guess it stands for quotient, quotient of two natural numbers. So this is what you would call a theorem of the alternative. It says, in general, if you have a rule satisfying a rule satisfying the three properties, one and only one of these two things can be true. The first one is what I just showed you. It's an example of, so I'm looking now at profiles. I'm going to look at profiles where there are only two things that are receiving votes. That's just to keep things simple. But you can think tax and no tax. Okay, so there are two possibilities. Either, this shouldn't be W here, so actually just ignore this. I'm going to explain it in words. Either every time tax and no tax receive at least one vote, and those are the only things receiving votes, the outcome is always the same. Okay? So no matter how many people vote for the tax and no matter how many people vote for no tax, I'm not going to switch the outcome. Okay, so that's one possibility, and that's the possibility which occurs here. The other possibility is that there's an injective mapping. So injective means one-to-one. That means every rational number gets mapped to a unique element of x. Every rational number in the unit interval gets mapped to a unique element of x. That means the outcome, or the image of this, has to be infinite, right? Because the rational numbers are infinite. Then what I'm going to do is essentially I'm going to look at the profile. I'm going to find how many people voted for one of the alternatives. So let's say, let me pick Z and W as my, let's say I'm looking at Z and W, and I'm looking at people who vote only over Z and W. Okay? I'm going to have this function that takes the proportion, this is a fancy notation for the number of people, the proportion of people who vote for Z. And the outcome of the rule is a function only of the proportion of people who vote for Z. And it's an injective function of that. So if the proportion changes, the outcome has to change. Okay? So you have to, as soon as I allow for an infinite set of alternatives, I get this possibility result. But the possibility result requires that even for a given pair of alternatives, right, when everybody's voting only for Z and W, that there's an infinite set of possible outcomes, depending on the proportion of people voting for Z versus W. Okay? And I tried to argue that this is exactly how proportional representation works. So I should go back. I call this gerrymandering proofness, but there is a mathematician, those of you who studied math, a very famous mathematician named Kolmogorov who invented this property 100 years ago. He didn't connect it to gerrymandering, and he didn't. Okay, 200. Oh, he was just born. Yeah, he was just born. Yeah, but statistician, mathematician, whatever you want to call him.
The one who put a lot of
He invented probability theory. No? Right?
He didn't invent it, but he put it on axiomatic basis.
That's what I mean by invented. This is a semantics thing, right? Yeah, but he invented this, and he used these properties to axiomatize the arithmetic mean. Okay, so the way I think of this is, one example of this is if x is equal to the unit interval, one example of a rule satisfying all of those properties is just the arithmetic mean. Right? So I just add up everybody's vote and divide it by the number of people who are there. And I like to think of that as, in some sense, proportional representation. So if I have everybody is voting for 0 or 1, right? Then the outcome of the vote is the composition of the governing body. It's, let's say, how many people, if 0 represents Republicans and 1 represents Democrats, the outcome of the vote would be the proportion of people in the governing body who are Democrats. Okay? That's the way I want you to think of it. At least that's the way I think of it. Okay. This is the hard part of the talk. I'm going to move on from here. So this is the math part. Well, the other part's kind of math too, but it was, you know, it's. Are there questions about this? This is just saying that yes, you can do something, but you have to allow for this infinite set of possible outcomes, which you may or may not find compelling depending on who you are, where you're from, whatever. The other thing that we do, and this leads to the stuff I did with Alan, and this is where I'm a little less knowledgeable. We talked a lot about restricting the rules of how things are done, or how people are grouped into committees, or this kind of thing. And that's what the people do in the gerrymandering literature as well. They try to restrict what kind of shapes a congressional district could look like. And what Alan and I did was propose yet another restriction on shape. Okay, so this is compact and contiguous. I'm not really sure. This is legalese, right? I don't know what it means. That's one problem with, working with a lawyer. I never really know how to explain what he's talking about, right? But there apparently, so the Constitution has apparently, I haven't read these. I don't know how to read it, but they apparently put some kind of restriction on the shape that congressional districts could have. This compactness and contiguity is one interpretation. No, I'm serious. It's very hard, right?
I teach those cases.
Oh, you know what they say then? Okay. They're famous then.
They are.
I've heard of them a lot. I don't know exactly what they say. Contiguity, that's just a mathematical concept of pathwise connectedness. Compactness, it's not clear what that means, right? And one idea would be that a violation of compactness would be something that looks like this, like a really long, kind of weird, normal shaped but very long district. That's not the notion that we're going to take. We're going to think of the idea, so if we go back to these pictures in the very beginning, we're going to think that these things are non-compact. So things that have a very strange shape.
You mean convexity?
That's what we mean. We're going to mean convexity. That's what we're going to take. We're going to take convexity as a benchmark. So if you want to think of something that's somehow looks gerrymandering free, if you want, convexity would be a benchmark in our environment. We don't have an axiomatic justification for it. We tried to come up with one. It's as compelling as anything else, I think. That's the only argument we can give. So.
Of course, you run into difficulties.
Oh, you run into difficulties with everything. So and this is William Vickery's example, and you can limit gerrymandering by putting restrictions on shape, but of course you can't stop it, right? And so this is the William Vickery example. So this is a state. Does anybody know what state this is?
Looks like Arizona.
It's either Colorado, Wyoming, something like that, right? Okay, here are the people in the state, the political parties. It's like a checkerboard. Yeah, Kansas. Yeah, it looks like Kansas. That's about right. So here, if you draw the districts like this, you get 2 seats to each party. Okay, you guys have seen this example? This guy won the Nobel Prize for the second price auction, right? But he also did some gerrymandering papers. Pretty obscure, but Okay, here all the seats go to the black party. So depending on, you can draw these districts in a nice convex way, and depending on how you draw them, you can influence the composition of the governing body. Okay, so here all the districts, they're all rectangles. So this is, I mean, you can construct all kinds of crazy examples like this. It's not difficult.
They're lovely examples, wow.
It's beautiful, right?
Look at you in there for, but they're certainly not humdrum.
It's nice, right? Yeah. Yeah, so what we're going to do is invent a measure, or a collection of measures, and you guys are free to pick whatever you like out of the family. And the problem with most of the measures that exist today, or until these papers, they didn't take into account population density, and they didn't take into account the boundaries of the state. And so you would end up with these congressional districts that had a bad shape, but they couldn't help but have a bad shape because the state they were in had a bad shape. So the way, I have this example about Maryland, and you have the western edge of Maryland. It has this ridiculous looking, yeah, but you know, Maryland can't help its bad shape, and you can't.
I don't think we want to.
Yeah.
It's a source of pride.
So what are the some of these guys I think are lawyers, so I don't know, some of them are political scientists. I think these guys are political scientists. At least one of them is some kind of physicist. Length versus width. So there are basically two major classes of measures that have been proposed. One kind of tries to measure how spread out, in some sense, a district looks. So you have things that look at the maximal length, and then they look at the maximal width and take a ratio. Or you have this one here, which compares the area of the congressional district to its smallest circumscribing circle. And this other one, this moment of inertia one, which is a bit weirder, but where you find the center of gravity, and then you normalize and find the average distance from the center of gravity to the perimeter as you go around in the circle.
That's just variance.
It's a kind of variance. That's right. It's a kind of variance. Yeah, that's.
And you're trying to keep the variance.
Yeah, that's what. That's. Yeah. So here, this one, right, the ideal shape would be a circle. Likewise with this one. Now the perimeter, these ones don't work so well, at least I don't think. The perimeter ones work slightly better. So kind of the standard one, it's the Schwartzberg. You take the perimeter and you take a ratio of the perimeter to the area. And the idea is that the smaller that is, right, the better. If you have a really long perimeter for a small area, it looks like you got a real problem, I guess. Taylor's measure, this one is, no, it sounds natural, right? You take so Taylor's measure, this is the weirdest of them all. Is Taylor here? Taylor's not here, right? Yeah, this is a really strange measure. This one, in fact, I'm not really sure how to operationalize it except for special examples. Kind of, you take your boundary and you count how many inward dents there are, and you count how many outward dents there are. So let's say something like this. And then I think you subtract the number of inward dents from the number of outward dents. So it is, yeah, I guess that's what it is, right? It's more or less like a measure of fractal dimension. But I don't think he called it that. So this is the Harris measure. I haven't got to our measure yet. I still have some time. Find the longest axis in the district. Find the maximum length perpendicular to that axis. Take the ratio. Okay. And so I'm going to go over some examples. This is a perfectly nice shape, right? This is achieves the perfect score. This one does not achieve as good of a score, right? The base is twice as long as the height here. So this is more gerrymandered than the first one. This one achieves a perfect score, right? As the length and the width have the same area. And so this one is better than the triangle, according to that measure. This one is a perfect score, right? So this is, you see, it's kind of like a strange thing to come up with these examples, but that's how the game works. So area of the minimum circumscribing circle. So this is, I don't know how to pronounce the guy's name, Roque maybe. You find the area of the district, find the area of the minimum circumscribing circle. So you guys know that every shape in some sense has a smallest circle that contains it. You guys know this? So then you just take the ratio. And this moment of inertia one, that's the one Don said it's a variant, it's some strange thing. These ones can be weighted, this latter one at least, can be weighted by the population, right? Because you can, instead of taking a center of gravity, you can take a center of population. But these also don't work very well, so it's the same kind of story, right? This one does better than this one according to both of those measures. And that's problematic, right? Would you agree? This looks bad, right? It's like a snake, and this one is, okay, they both have the same area, same convex hull. This one does better, yeah?
One question
Yeah.
about this one
Yeah.
being worse than the other. This one being better. Okay, this is the worst one. Go back
Yeah,
to the other one.
yeah,
That's the better one. Okay,
yeah.
but it's got to be the case
Yeah.
that the flip side district, which includes the white spiral,
It's probably way worse,
gets a
right?
horribly low score.
Probably.
So even though that gets a great score,
Yeah, probably.
it creates a district that gets a terribly low score.
Fair point, fair point.
Well, if the spirals are the same width, if we adjust that figure so that the spirals are the same width, it's still getting a pretty okay score
Oh, is
relative
it?
to how bad
Yeah,
it
they're the
is.
same thing.
Oh.
They're carbon on each other. He's got a real
Yeah.
small, but as Thomas is pointing out, that if they both have the same width.
Yeah, that's fair. That's fair.
But this is good. This goes to a conjecture Alan and I had that at some point, if I have time, I'll talk about. But,
Well,
whether we want to look at these things as individual districts or whether we want to look at them as pieces of the whole.
Well, no, but
right?
just to respond to that, but the likelihood is that that's not an entire district. So in other words, that white part's going to be attached to some shape outside that square. Is it still going to get a high score?
If you
I mean,
then
a low
attach it
score,
to
a good
something
score.
that's further out there, but I mean, I could like take a map of Charlotte
Right.
as a city and basically divide it into two spirals, and then the two spiral districts on top.
And they would be well
And they would
scored.
both be fairly good as far as moment of inertia.
I'm sure you can construct
Yeah,
weird.
yeah.
You can construct. The whole point of this literature is to come up with a measure and then construct a weird example. And you can do that. You can do that for our measure too. I mean, someone already did it, so it's already in the literature. So we suggested that if you take two identical towns and string them together with a small narrow path, that the stringing the identical towns together should be worse. Right? So this one should be worse than this one. Right? This is a nicer shape than this. Most of the measures I just talked about, they actually violate that test. Right? This one would be better than this one for almost every single one of those measures. So this is a kind of axiom we'd like to capture. The one we're going to invent is called the path-based measure. I'll talk about it later. The Schwarzberg, that was again the perimeter to the area, and the Taylor was counting the inward and outward dents. So you can see those ones kind of, at least for the Schwarzberg and for the counting the inward and outward dents, you're doubling the number of inward dents and outward dents here, and you're also doubling the perimeter in area. So it's not surprising that one gets worse. So this is Polsby and Popper. I know that there's a Polsby that's a lawyer because I heard someone talking. I don't know if this is.
That's probably Nelson.
This is probably a different guy, and
It's his brother.
and this is not Karl Popper. This is some other Popper. This is the guy I'm usually talking about is Karl Popper, but this is some other Popper. It could be his son. I don't know. But this one has a problem, and the problem is it's not continuous in a natural sense. So we have this way of measuring distances between sets. It's called the Hausdorff metric, and it's just a natural way of measuring distances between sets. And you'd like, or at least we'd think you'd like a measure to be continuous in the Hausdorff metric of the boundary of the set under consideration. See, what you have here is something that looks like a square, but if you remember geometry, the perimeter of this thing is square root of 2 times the perimeter that the same square would have, right? Because you've got these little city blocks here. You see that? So the perimeter is longer. Well, because the perimeter is longer there, this one is the absolute worst out of all of these. Right? That's the problem. So this thing is not, it's not appropriately sensitive to small changes in the boundary, which is, yeah.
But if we're looking at sort of gerrymandering as an issue, one of these major issues is having that very small, geographically small inclusion or exclusion that's very irregular,
Mm-hmm.
just to deliberately, oh, this is this very high population density node that
Mhm.
votes this way.
Mm-hmm.
So if you have lots of little fidgety details on the boundary edge, it could be a sign of some very careful work along.
Probably not in this case, though, right? Could be. It could be. Yeah, you don't know. We don't know. But we have no reason to say that. It looks like this is more likely to be, right? If these are houses, think of these as houses. You've got your neighbors here. You know, here you don't have your neighbors. So it could be. So the path-based measure, that's the one we're going to introduce. This is Maryland, right? These are the mountains here. This is a population. That perimeter measure, this gives this a horrible score. But why? Why? Maryland shouldn't be penalized, right? It's not Maryland's fault. Hey, this is a perfectly nice shape right here. This is some river. It's a perfectly nice shape. It's pretty smooth looking, right? They just cut the western side off. Why give it such a low score? It doesn't sound right, you know? So the story is the measure we're going to introduce actually gives this a very high score. Gives this a very high score. So what's, and the same thing goes for here. This is a case where our measure actually gives a higher score to this. The perimeter measure gives this a low score. I don't want to talk about these examples too much because I haven't really got to our proposal yet, and I only have 20 minutes left. Oh, one more example. This one has come up recently by Roland Fryer and Richard Holden wrote this paper. The original guy to invent this model is this guy named Papayanopoulos. And this is a measure that applies to an entire districting plan. So you look at the whole state. Okay, and you look within each district, and you sum all of the distances between each pair of individuals. Okay? And then you add those up across all of the districts. The problem is this one tends to not penalize urban gerrymandering. And I'm going to go over the example. So here, this is the countryside. This is a farm. See, there's not many people living here. This is a city. This is New York City. Okay? I'm going to give you 3 different things here. This looks pretty nice, right? And this looks okay. This looks terrible. Right? This is a problem. Okay, so these measures are going to say this is the best, this is worse, so that as it increases, you get worse with these measures. This is the worst of them all. We got a problem, though, because this one's now better than this one. Right? But here, this seems, everyone would agree that this is gerrymandered in a worse way, because we agreed with that up here. Then this, so the gerrymandering in the city is worse than the gerrymandering in the farmland, yet this is still ranked better. Okay? So this promotes urban gerrymandering. When people tend to live close together, this thing doesn't work well. That's the criticism. Okay, I forgot this. So our approach, we call it the path-based measure, and you can generalize this in an infinity of ways, and we've done that. How many people have heard of convexity? I don't know. I mean, convex shape, pick any pair of points. The line connecting that pair of points is in the shape. These are convex. You see? You pick any pair of points. These are non-convex. Just means you can pick a pair of points whereby the line joining them does not lie in the set. These are non-convex, right? You can pick a pair of points whereby the line joining them does not lie in the state. And this has something to do with Shaw v. Reno, the Rorschach inkblot test. Maybe that's what these look like. I think that's the. This is straightforward, right? Is this okay? So our measure is going to be a measure of convexity. Well, that's going to be a dumb measure if we just say, oh, this is non-convex, throw it out, right? Because nothing's going to be convex except maybe when you cut Wyoming into 4 squares, right? Colorado, you know, Kansas. Kansas is not convex, is it?
So,
Maybe it is.
South Dakota both.
Yeah, North and South Dakota. Yeah, but they probably only have one also, right? Yeah. So A district, we're going to have a measure of convexity. A district is convex if it contains every line segment containing its points. We're going to imagine that you randomly draw, so IID, you randomly draw, and uniformly from all the points in the district, you randomly draw a pair of points, and then you check the overall probability that a randomly sampled pair of points lies in the district. Okay? So scores range from 0 to 1. Score of 1 is perfectly convex.
Is that used anywhere? Did you guys just invent it, or is that?
We thought we invented it, but there's a reference in the paper. We found some obscure set of computer graphic notes. So some other people are talking about this. It was unpublished, but we referenced it.
Doesn't have a physical interpretation issue.
I think it was Ehud Lehrer who said this would be interesting for measuring how nice an opera house is. You know, if you can see every point from it.
Let's flashback that definition, your criterion again.
Yeah.
I'm sorry.
So I'll try to, this is the problem with Alan, right? He puts these things where you need like 1 million clicks. It's on tape, he'll hear it. We're going to just randomly pick a pair of points.
Okay.
Yeah.
I'm sorry, just
Yeah.
flashed too quickly.
Yeah. So what's nice about this one is we think it has a nice normalization. So a town that's perfectly convex has a score of 1. 2 towns strung together with a narrow path has a score of 1/2. 3 towns strung together with narrow paths has a score of 1/3. So if you have 1 over n, it's approximately equivalent to n towns strung together with a narrow path. That's the way we think of this. Okay, so it's just a kind of a normalization. Okay, what else can we do with this? What can we do? These 2 districts have the same shape, so they get the same scores. But now we're going to put people in them, right? No, this one's way worse. This is much worse because these 2 arms reached out to pick up these people out of nowhere. This one, they're just picking up the woods here where nobody lives. So which one's worse? This is worse. That's our argument. So instead of looking at randomly selected points, we're going to look at randomly selected residents. When you look at randomly selected residents, this one is going to have a score of 1/2, and this one's going to have a score of 1. So now we have a method of talking about incorporating population. Okay. I said the other problem with the existing measures is state boundaries. How do we do this? You know, all these other measures, you're taking the perimeter or whatever. How do you normalize that with respect to the exogenous boundary? Well, we're going to take, instead of the straight line joining 2 points, we're going to suggest taking the shortest path that lies in the state that connects any pair of points. Okay? So the probability that the district contains the shortest path in the state between a randomly selected pair of its people or points. So if you take this point here and this point here, okay, the shortest path goes up here. I think this thing's like 1/2 mile wide. And then it goes down through there. And that actually lies in the district in this case. And so that seems more relevant than something that cuts through, what is this, West Virginia or Virginia or something. So that actually gives us a pretty high score. It's not that gerrymandered. And this is another example. This is Arizona. You see, I don't know how this is pronounced, Laughlin or Laughlin, or I don't know. Bunkerville. The shortest path connecting that pair goes here. Okay? And that actually lies in the district, but the shortest path connecting Laughlin and Paradise goes outside of the district, which is in the state, goes outside of the district. So this is essentially our proposal. I don't have much else to say. There is some generalizations. So one generalization would say, and our measure is an all or nothing thing. It says look at whether or not the shortest path connecting 2 people actually lies in the district. You could also imagine looking at how much, or the extent by which the shortest path in the state is exceeded by the shortest path in the district. Okay, and then take an expected value of this function. And as p could go in between 0 and infinity, as you take p to infinity, it's the one I've been talking about. This is the other thing that I think we did that's relatively new. And so this has something to do with some state laws. I'm not sure which states. Probably California, probably Maryland. Our approach here, we can generalize this idea further. So we had this idea of taking the shortest path connecting a pair of points which lies in the state. Well, now we can generalize that further and say, well, now I'm going to look at a set of admissible paths, things that I think are admissible between a pair of points. And so one idea might be, and this is the idea that I like, so, you know, if you're living here, and there's a guy living here, and this is 10 feet apart, but, you know, here's the Grand Canyon. Okay, it's 10 feet's the wrong, let's say 1,000 feet, 10,000 feet, whatever. Here's the Grand Canyon. All of a sudden, they're not so close anymore, right? You might have a road that goes way, 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 way over here that connects them, and the road is, let's say, 5,000 miles long. Okay, that's also an exaggeration. But you had to go to New York and back, right? But this would be then, if this is the shortest road connecting the pair of people, this is what we would say is an admissible path if we cared about road distance, right? Or if you had shortest train, that's probably right. So there are ways of incorporating this generalized notion of admissible path, right? So the case of where we care about state boundaries was when the admissible paths would be the shortest path that lies in the state connecting a pair of its residents. You can do the same thing with roads or pre-existing congressional districts and such. So that's basically all I have to say. I just want to go over these sensational examples again and take a look, and then we'll stop. There's got to be a conclusion. Yeah. So as far as I know, this is the first measure that both takes into account state boundaries and state population, which we thought was an interesting contribution. I guess the problem is whether or not you think this whole measure of convexity or measure of gerrymandering is interesting, and it can't be the whole story, right? I mean, there's no way it can be the whole story, but maybe it can be part of the story. But as soon as you invent a measure, somebody invents a computer algorithm that finds the best thing. So it's only part of the story, right? This is so I'll stop here and see if there are any questions about the general approach. And it's actually kind of an active area, so I don't know much about the legal aspects of it, though. But I'm happy to discuss, yeah.
So, yeah, it's hard to bring up a lot.
It's okay.
I'll mention a couple of things. One is, and I'm sure Alan's thought about this, but since he's not here to defend himself, I'll just throw this out there, that the Shaw case is a bizarre case. And it doesn't really articulate the rule that you're claiming it articulates.
No. We don't. I don't want to claim this is the interpretation.
No. I understand,
okay.
but it does raise. But understanding what it says is relevant to the project. So I'm going to briefly say this if you don't know it. You had this very strange claim by residents in North Carolina's District 12, which had kind of volleyed up and down the system, got to the Supreme Court in a few different cases, and these claimants didn't allege what their race was. Whether they were white, black, they didn't allege their sex. It was really kind of anonymized. And they raised the claim that the district in which they resided was so bizarre in its shape as to be explainable on no grounds but race. That was the claim. It's so bizarre that when you look at it, the only way you could actually comprehend this really strange-shaped district was this must have been done to accommodate race, which grows out of the Voting Rights Act, because there's a principle in the Voting Rights Act, which was partly affected by this recent Supreme Court case, Shelby County v. Holder, that has a principle in it called non-retrogression, which is to say that when you have a decennial the decennial census, the states get reallocated their congressional seat counts, and then they do their redistricting. And the principle was that for so-called covered jurisdictions, that's what was at issue in Shelby County, you couldn't retrogress, meaning lower the relative representational power of minority groups, primarily African Americans. So a lot of this stuff has to do with that. The Shaw case is this bizarre case that didn't claim the line was specifically drawn for that reason, but said there's no way to explain it but for race. And what happened was, O'Connor writes this opinion, and she analogizes it says it's been analogized to a Rorschaching plot, to a bug splattered on the shield of a windshield, driving a car driving 85 miles an hour, all these kinds of things. And what she says is that if in fact you can prove that it's so bizarre that it can be explainable on no grounds but race, you've stated an equal protection claim. In the course of that discussion, she offered to the states ways to defend their districts against equal protection challenges. And she included 3, of which you've listed 2, compactness, contiguity, and respect for political subdivisions. So these aren't constitutionally mandated requirements. What they are is, in a sense, things that if states are able to demonstrate at some level, insulates them against an equal protection challenge. The real problem with gerrymandering, and it's worth thinking about, is that the reason we have these bizarre districts is because the states are confronted with 2 sources of legal authority that directly contradict one with the other. One is that they have an obligation to comply with the Voting Rights Act and not retrogress. So they have to come up with districts that preserve minority-majority districts. But on the other side, if they do it overtly, then they run up against a claimed equal protection violation.
What a mess.
So they have to actually draw the districts in a way that don't retrogress, but draw them in a way that they can defend for reasons independent of race. And the combination of those things, which is where another case comes in, Bush versus Vera is about trying to defend a district for reasons other than race. Yeah. The combination of those 2 things results in these truly bizarre districts. Okay, the reason I raise all that is not to really teach common law here, but rather to raise this question. Why do bizarrely shaped districts bother you? And I actually think it's a question that matters.
Psychology, no?
But who cares, right? In other words, it's a really interesting thing.
The media cares.
Cases,
you guys all laughed at the pictures, no?
No, I get it, but I guess the question isn't who cares, the question is why we care. There's an interesting opinion by Stevens in one of these cases, it might be the Bush versus Vera case, where he writes a separate opinion, and he says, what does bizarre actually mean? Imagine you're in the state of district and you've got a sea of bizarre districts, and you superimpose smack dab in the middle of those sea of bizarre districts a square, which is the bizarre district in the state of Texas at that point. Right? And it's a good question, actually. It's all obviously about baselines, but I do think that it matters why the odd shapes, other than the amusement of it, is bothersome. What I really think is going on with these bizarre shaped districts is we're in a sense replicating something that in parliamentary systems are not geographically districted. So we're trying to connect up communities of interest, except the way we do our election system, they actually have to be contiguous districts. And so in order to assemble communities of interest, we have these weird things going on. Whereas if we were in our parliamentary list election system, then the effective district supporting a particular party would be non-contiguous people all over the place. They would vote, and the party that gets the largest number of votes, or proportionally, you would go down the list. The constituency for the representatives in the parliamentary list system would be a non-contiguous district, right? So what's really going on is we are constrained by virtue of our constitutional system to geographical districting. We're trying to achieve the goals, since ideology, race, and other things connect people up more so than geography did 200 years ago. We're trying to come up with a geographical solution to assembling communities of interest that would work well if we weren't geographically bound. So what we're really doing with the weird shapes is trying to come up with something that's quasi-parliamentary in a geographically limited district, which comes back to the question of, do we, other than the amusement or the peculiarity, I'm left with the question, I struggle with it. Do I really care if it's a bizarre district? Just for the sake of its bizarreness? Or is there something else that correlates
It's
with
supposed to be,
bizarreness
yeah, the
that I
idea,
care
that's the
about?
idea. We haven't done any test on that.
Oh.
We'd like to know, we'd like to, at one point we were talking about checking the, whether the bizarreness was a measure of non-competitiveness or we could correlate it with something
Yeah.
like that.
Well,
We haven't done any empirical. Yeah.
Isn't the underlying notion here that if I gerrymander it right, which is arguably what the Republican Party did really good job of
Right. In Texas, yeah.
well, really across the country,
Yeah.
you can make it such that it's no longer one man, one vote, it's like 3/4 of a man, a vote.
Well, I don't know, it's not really different from what Charlie was describing, right? I mean, you're doing with this redistricting what you're doing when you just restructure the vote. Now there we didn't feel we had any principles really to go on to distinguish between these different strategies. Although one interesting question would be whether maybe some of this can be translated into a set of criteria that would allow us to distinguish between some maneuvers as being more legit than others.
My reaction to this, the parliamentary, my initial reaction without really thinking about it, which sometimes is worse than I think it is, is that when I think about these connections about spatial, why spatial? I had this intuition that interests are connected spatial. We have local schools, we chat with each other, and you have local streets. We have all this infrastructure and public goods that connect us spatially. And so in some sense it's kind of natural to say, well, let's keep the meat or the source of information connected in a spatially way. Now, whether it's effective or not, but down deep as I read these things and I look at it, I come back to that idea that it comes back to right or wrong. A lot of our public interests are, as a matter of fact, spatial. Now, of course, you can cut that a lot of different ways now, with internets and all kinds of connections and communication. It could be that our interests are quite different,
Yeah.
but historically
Absolutely. I agree.
and physically, maybe
Yeah.
even still,
Yeah.
there's a geographic, physical connection between our interests. Now, that doesn't mean we're going to use your metric.
Well, you had a interesting, gerrymander proved this. And I was wondering why you didn't go back to that. Stating here is the rule, majority vote or something else like that,
Mhm.
plurality or whatever you would like.
It's symmetry.
And
And
then-
symmetry. Almost majority rule because it's a symmetry
Yeah,
function.
but then the question is, which rule satisfying, say, your condition will come closest to satisfying constancy of this rule right here. You're not going to get equality for the simple reason you already proved that you're not going to get equality. But it comes closest to satisfying that because that gets up to what Max was saying in terms of the political division. And you have in there geographic and people, but you don't have the political division. You still, I'm pretty sure that for a little while I can sit down and look at your test, and I bet I could get it so I could skew it so there'd be more Republicans than Democrats or more Democrats than Republicans.
Yeah, I think so.
But if you had your condition, the
Yeah.
condition you started off with,
Right.
saying that you have to come as close as possible to matching that too,
Yeah.
that would be another condition for the political subdivision.
I mean, what I'd like, and I know this is impossible, but I'd like them to just write down a law and says, here's how you do it, here's the algorithm, that's the end of it. It doesn't work that way in politics.
And then
What would
argue.
be, I mean, I'm wondering
Increase your consulting fee.
how, what if we had a system which took all the voters in a state and just packaged them randomly into, equal sized district with no attention whatsoever to geographic contiguity?
And then what's
did
the
it so
point of having the
randomly so there's no
representative
manipulation?
system?
Sorry,
What's the
what?
point of having the
Equal size
representative
geographically?
system?
No, numerically.
Well, because they're all equal size numerically. I mean, that's constitutionally mandated.
I know, but
Yeah.
then of course we've eliminated all
Yeah.
possibility of manipulation and.
But the whole point of having the district is because people who live near each other have similar interests, right?
Well, that's
Historically.
Now, why do we care about that?
Well,
That's
why have the representative system anymore? Otherwise, why just get rid of it? No.
No, I don't see why that follows.
I think
If
it's
you would have a
because
representative system
the
without
governments are supposed to
continuity.
solve certain kinds of public goods problems.
Yeah.
That's the reason presumably we have them. And so you have to get the locus of where those desires for public goods might be.
Well, we're talking about congressional districting. I mean, yes, it also applies to state districting, but you're talking about congressional, federal
Yeah, that's what
congressional
I,
districts.
right.
So it's,
This is not
it's
the
less
way
about
I
providing
understand
in-state public. When you're talking about the
State.
gerrymandering for the state of California for the general,
That might be
then you
Yeah.
get a different dynamic.
Hard-
And you do have
hard-
similar constitutional
harder
principles.
to make that argument
Yeah.
for the feds.
Yeah.
Seems like it just has more bureaucrats.
Well, the trouble with doing what Leo is saying is that, look, get a smart computer person there, and they're gonna, for a certain fee, they'll be able to fix that computer to gerrymander it the way you want to gerrymander it without anyone knowing about it.
I mean, I've heard of it.
It's not transparent.
I heard of some system, and I don't remember where this is, where people actually got to choose which district they would be in. So districts were just indices, and you could join with your friends in some district, and then you could decide. You know?
That's T-Bow, that'd be a T-Bow.
What is it? It was,
It's
like a T-boom model, yeah, it's like a T-boom, right.
What it is that the geographical contiguity, or what you call a common interest, does for us. I mean, so surely, I mean, the extreme cases, we would think it absurd to appoint someone governor of a state in which every citizen was located somewhere else in the
Right.
country. But exactly why? I mean, right? Why it's so contiguity clearly matters in that case. But is it because there are things, people are contiguous, there are resources in dispute between them that he allocates, and that's not likely to happen if they're distributed in a disconnected way? I'm not.
I could imagine information arguments, by the way.
Well, there are kind of examples. I mean, Scott Brown was about to run for the New Hampshire Senate. Why? Because he can get elected there, having been voted out in Massachusetts. Hillary Clinton did run for the New York Senate. Why? She had no particular connection to New York, but she thought, you know, so I mean, so but that is equivalent to voting for people who really live in another state. They really are going to live in D.C. after they're elected, and they'll occasionally come talk to you because they have to have an in-state office and satisfy a rule. But the idea that they're from your state, well, not so much, and they're funded from out of state.
There's a state assemblyman in California that's just convicted on a felony charge for not living in
Yeah,
his
for not living
district.
in the state.
This is not living in his district.
In
this
this
is
Yeah,
the
yeah,
assembly.
his district, yeah.
And the rest of the state assembly is reluctant to kick him out. Because it turns out that lots of them don't live in the state district. I mean, maybe they've got some kind of a room there, but if you scratch the surface a little bit, they don't live there. And yet, I mean, this is it's felony conviction.
Yeah, it's serious.
It's a serious thing, so for some reason.
But
it's
felonies usually are very
most of them, right?
This speaks to a really interesting broader problem, and I want to thank everybody. This has just been amazing. I have some very practical problems to address, and this discussion has addressed a number of them. But when you come up to the complexity, and we put all this together, including this, there's a common denominator here. We need to be path and partition independent, but we have to be governed by something. And every time we add some sort of defeasibility rule or something, we increase the complexity, and without worrying about what specifically we do, that complexity leads to randomness and chaos and so on. There is a precedent in corporate law that used to be called the prudent man rule, the reasonable man rule. And in the 80s, we had to worry about that as directors because you would go to jail or get stripped for being imprudent, and we had to define that for ourselves, but the real test was what would a reasonable man do? And the joke was that in the Wall Street Journal, there was an ad said wanted director should have low net worth. The issue, though, really focused you on being good. Now, again, as I'm told by the guys that advise me, our companies listed in Delaware have absolutely no responsibility left because this really good principle has been watered down, I assume, by precedent, to the point where the bar is so low you would have to shoot somebody in a boardroom in front of witnesses, that was the example given to me, for actually getting into trouble. Now, what has that done? The fact is it's destroyed a perfectly logical and very important thing, but what does it mean in the abstract? It means that when we take these highly complex issues that are totally indeterminate, and we try and invent by fiat a determinate solution for them, we end up with this infinite dimension of complexity that gets us nowhere, and precedent then plays the game. So we get this situation where nobody's living in their district because they can think they can get away with it. The minute you bring back this precedent in some way that can resist this gerrymandering of the precedent, you've got something that really works and did work, and today nobody cares. There is no prosecution, literally, of any white-collar crime at the director level and so on. Well, this is destroyed, as I said before, my problem builds on the patent issue to general law. The law doesn't exist for us. We just fuss about how we're going to deal without the law. To bring back the law would be fairly straightforward if we can re-invoke the prudent man rule in some meaningful way. But what does that mean? It means a judge or a jury or some collection of people have to decide what reasonable means. Well, that's what they did before, and it kept all of us honest, and the board accounts here if you want to deal with different issues and how important they are to people. But that's a feasible solution, including to this, because when you ask the question, Max, why do we care? We're really forced to say, well, what's reasonable? Now, people can debate it, but at least you can't get away with saying, screw this, I'm going to live in Florida even though I represent Massachusetts. The real issue is, how do you keep aggressive human behavior at bay? Everything's a trade-off. But this prudent man rule was very powerful. How do we bring it back? That, Chris? Well, I'm not asking Chris.
Don't ask me.
Which is path dependent.
Well, actually, though, if I can build on that for a sec, maybe the reason you want a geographic district, see, the problem is, if it's the public goods, you can say, okay, the local public goods can be dealt with by the local government, and the national government is doing something else.
That's right.
But if you require the national representative to live in a particular place, then maybe he is not going to get as corrupted because he's got neighbors that he's supposed to be representing and they're looking at him. And if it was just a random labor list or whatever, the guy wasn't your neighbor, you wouldn't be looking at it as much. I mean, it's sort of, why is it that a geographic district might be useful, right, for a national decision?
Well, we see these local things elevated.
Yeah,
When
well,
there's local
but
things that are
actually,
elevated,
what's,
so they take action at the national level, like drugs, marriage.
Yeah.
well, the other thing is,
Things that are local interest to start
given the
with,
way
they
that
were
this is
into.
going, the national government then is actually doing plenty of local
Yeah.
stuff, and maybe that's
Yeah.
not to the advantage of efficiency either.
But if you subject that to the reasonable man rule, you start asking, in Timothy Wilson, you know, the unknown to ourselves, he talks about changing the conversation. You want to change behavior, change the conversation. We, by forcing ourselves to think about reasonableness in whatever judgment is specific to the institution or the condition, you actually start invoking good behavior, and that's ultimately, I think, what we want.
Okay, so I'd like to sort of bring it back to some things that you said, and you just touched back on again, why do we have geographic districts? And one of these driving factors on why we have trouble with the districts, and I don't think it's actually very responsible for most of the ones that we saw on the board, especially you look at the North Carolina 2010 districts, they're a mess even compared to, you know, you previously had in the 80s and 90s, you have one or two districts that look a bit weird, and they're weird for a clearly identifiable reason. In 2010, they all become very weird very quickly, and it's because the Republicans had the state legislature for the first time since Reconstruction. That's a conflict of interest problem there in terms of who's drawing the districts rather than, but this minority representation issue is one of the motivators for having a geographic district is that you have minority interests that are geographically located. Here's where lots of Quakers live, here's where lots of black people live. And if you're electing from, say, I take random samples of units of 500, 600,000 people from around the country, that's going to produce, by statistical sampling here, that's going to produce a significant underrepresentation of every minority group in that Congress. So if I draw together 600,000 random people from the United States, I can give you to within, an expectation of 2% of what the racial composition of that district is, of what the political composition. I mean, at least they would all be politically competitive in that sense. Of most of them would be between 45 and 55. But
Wait, can I just respond to that for a moment? So I want to be clear, I'm not advocating that we switch our constitutional system to a parliamentary system. I don't want anybody to come away with that impression. I'm making a positive observation that part of the dynamic that creates the disconnect between identifiable geometry in the districts that we see is because there's a path dependency here in the following sense. Historically, we were more grounded in geography. Geography was destiny. The framers of the Constitution viewed geography as destiny. That's just no longer true. Instead, interests tend to align in ways that are, frankly, prioritized by criteria that eclipse geometry. Geometry is no longer our primary identifier of self. And so, but if we were to have a parliamentary system, part of the difficulty with the claim that you would have substantial minority underrepresentation is, in fact, a parliamentary system would be a multi-party system, not a two-party system, because there'd be competition among coalitions that would form after the election to create a majority. That's the way parliamentary systems work. And so you'd actually have the emergence of smaller parties that could in fact represent subgroups. And you see that in countries that have parliamentary systems. They tend to be multi-party, not two-party, with some exceptions, I acknowledge. But it's a different system. Again, I'm not advocating it. I'm simply making the positive observation that the reason we see it is because geography doesn't do what it did when the framers conceived the original model of our system. And the only other point I'll make is there's a very curious alignment of interest that operates to the detriment of the Democratic Party between minority voters, African American voters who tend to be overwhelmingly Democratic, and the Republican Party. And the reason for that is that in order to preserve minority representation through non-retrogression, you have to group together African American voters sufficiently to ensure their effective representation in a district, which means you can't disperse them across districts to strengthen Democratic districts, and they tend to be highly Democratic. So the Republicans have more maneuverability room in these kinds of gerrymandering games. The Democrats are systematically disadvantaged by the relationship between the Voting Rights Act and these other equal protection principles. So it's a very complicated, as complicated as this
It sounds
account is,
complicated.
the law side of this is also enormously complicated. So anyways,
It's over my head, It's too
it's
complicated.
messy.
One of the nice things I like what you did, Chris, there is that you got away from just geography. You were brought in actually people. Which I had, but I really think that if you go back to your original comment in terms of things there, and to try to equalize that with respect to other things, I think you'll have something very powerful.
It could be.
Maybe if you rate the people by how much money they have, you'll be able to explain her.
I guess the way the system works now.
That's right, I was gonna say,
Yeah.
you don't have to do anything with that.
Shall we thank Chris?
We should thank Don, right? And Joanne is not here, but I guess we should.
Yeah.